Like this problem, for example. You have a cylindrical tungsten rod, length is given, its diameter is given, and we want to know what its length turns to if there's a 5,100 kilogram mass that's hung from the end of it, and Young's modulus is given. Well, let's solve it. I'm going to imagine this is my rod, and there's a weight hanging there, and that weight exerts a force, and that force is equal to m times g. And as that force acts on it, it's going to get longer. So it's going to grow by some length that's delta L. There's my rod now grown in length because of the force. Well, what I want to find is delta L, and that's in the equation for Young's modulus. Young's modulus is defined as F times L divided by area times delta L. Since I have the radius of this thing, I can find area. Length is given to me. Force I can figure out because it's mg, and so I should be able to solve this. What I really need to do is just isolate delta L because that's what I'm trying to find. So delta L is force times length divided by Young's modulus times area. Let's define a few of these things. First of all, force is equal to mg, and that's a 5,100 kilogram mass times our normal 9.80 meters per square second gravitational acceleration. And when you multiply those two together, your force is 49,980 newtons. So that's a pretty big force. Let's also find area. Well, area is pi times r squared because this is a cylindrical rod. This is a circular rod. It says that the diameter is equal to 5.00 millimeters. So that means the radius would be half of that, which would be 2.5 millimeters. And to keep our units all consistent, that would be 0.00250 meters. That's radius. So our area is pi times 0.00250 meters, and that quantity squared. The area turns out to be 1.96 times 10 to the negative fifth square meters. So now we have area, we have force. Young's modulus was given to us, and so was length. So now we can quantify what delta L is. Delta L is F times L divided by Young's modulus times area. So our force, well, that was 49,980 newtons. The length was 5.000 centimeters. Young's modulus was 3.55 times 10 to the 11th newtons per square meter, and the area we just calculated is 1.96 times 10 to the negative fifth square meters. So delta L, when we do all these calculations, it's going to have units of, newtons drop out, square meters drop out, it's just going to be centimeters because that's what we have for our original unit of length. And the answer is 0.0359 centimeters. So the length, which is what we're supposed to find, would be the initial length, starting length, plus the change in length. So it'll just be our starting 5 centimeters plus our 0.0359 centimeters of delta L, and that comes out to 5.0359 centimeters. Here's another example. We have a square bar, and it doesn't tell us what the material is, but we do have the dimensions. The square bar is 1 centimeter on a side. It's 10 meters long, and we know that it becomes 0.0318 millimeters longer with a certain force on it. So that means we know delta L. And our job now is to find Young's modulus for the material. Well, let's solve it. Young's modulus, by definition, is F times L over A times delta L. So let's calculate A first of all. It's a rod. I mean, it's a square bar. So and it's 1 centimeter on a side. So it's 1 centimeter here, and it's also 1 centimeter here. And a centimeter is 0.01 meters. So the area is just going to be equal to 0.01 meters squared, which is 1 times 10 to the negative fourth square meters. So that's area. Young's modulus then is the force well, that was 50,000 newtons that was being applied, times the length, the original length was 10 meters, divided by area, which we just calculated to be 1 times 10 to the negative fourth square meters, times the change in length. Well, it told us that the change in length was 0.0318 millimeters, so that'd be 0.0000318 in meters, which we probably want to put in here so that our units work out right. And the meters are then going to cancel out, and we'll end up with Young's modulus units of newtons per square meter. The numerical answer here is 1.6 times 10 to the 14th newtons per square meter. Those big numbers are typical of Young's modulus numbers. Let's take Hooke's law and look at a special case. Let's imagine that you have a solid of length L, let's call it length L, and it has a cross-sectional area that we'll call A. Just working in symbols here. Some solid. Well, Hooke's law says that stress is equal to Young's modulus times strain. But stress is F over A, so that's equal to Y times strain, but strain is delta L over L. If we rearrange this a little bit and solve for force by multiplying both sides by A, here's what we find. Force is equal to Young's modulus times delta L over L times A. Now there are some things for this special case that are constant, like Young's modulus would have to be constant because it's a characteristic of the material. It says that the length, the relaxed length, the unstretched length, is L. That won't change. And it has constant cross-sectional area, so that's constant. So let's take all the things that are constant, we'll just lump them all together. So Y times A divided by L, the unstretched length, those are three things that are never going to change. And then we're multiplying by delta L. So this tells us that the force is equal to a constant number times the change in the length. Well, this equation looks really familiar, and in fact, it's the equation for force due to the spring. F equals K times delta X, we said back then, but delta X and delta L could mean the same thing. So really, the spring equation was Hooke's law, just applied to a special case. And you might not think of a solid bar with constant cross-sectional area as being a spring, but it really is. It functions like a spring, as long as you don't go beyond the elastic limit of the material. One other thing that we should look at before we are done discussing solids is what happens to them when you heat them up. And it's very similar to what happens to liquids when you heat them up, except we can deal with only single dimensions at a time, too, with solids. One characteristic is that the length of a solid will increase in direct proportion to increasing temperature. So what that means is the change in length for a solid as a percentage of its original length, or as a fraction of its original length, is equal to a constant, we call this constant alpha, times the change in temperature. And this alpha here is called the coefficient of linear expansion. And it's going to have units that are going to be length over length times temperature, degrees C typically, or kelvins maybe. Well, if the lengths are given in the same terms, you could also say this is just 1 over degrees C, or 1 over kelvins. Another thing that we could say is that the area of a solid will increase in direct proportional to increasing temperature. So delta A over A, where A is area, is equal to 2 times alpha, it turns out, times the change in temperature. You've got an A this way and an A this way, so it's expanding in two different directions, and so you have to take into account for alpha twice. And if you do this for volume, a solid will expand in all three dimensions too, and you get an equation that you've seen before. delta V over V is equal to beta times delta T. And beta is just 3 times the coefficient of linear expansion. We saw this for liquids. It's true for liquids, but it's also true for solids. Well, here's an example that you could solve using the coefficient of linear expansion. You have a glass rod, its length is given, the temperature is given, a new temperature is given, hotter temp, and the coefficient of linear expansion is given, and the question is, what is its length? So here's the glass rod at 20 degrees C, and then it's going to go in an oven, and when its temperature heats up to 315 degrees C, it's going to get longer by some length delta L. And we know that this relationship holds true. Delta L over L is equal to alpha times delta T. So if we want to find delta L, just multiply both sides by L. So alpha, L times alpha times delta T is going to be the change in length. So we'll plug in the original length. It said it was 25.0000 centimeters. You need all those zeros because it's not going to change very much. Multiplied by alpha, now you're going to see why it doesn't change very much. Alpha was 3.3 times 10 to the negative 6th, and it's delta L's per degree C per L. Well, we're working in centimeters, so this is just going to be centimeters per centimeter degree C. And you can see that the centimeters just drop out of this. And then we're multiplying by the change in temperature. Well, it went from 20 degrees C up to 315 degrees C. So the difference, delta T, is 295 degrees C. So that's what I'm multiplying by here. All units drop out except the original unit of length. And when you calculate this out, you come up with 0.0243 centimeters. So the length, final length, was the initial length plus the change in length. So our initial length was 25, and we changed by this amount, so it's going to be 25.0243 centimeters. That's the final length.
Well, hi there, Mr. Eckstrom. You know me if you've been watching these videos. And I'm here with my friend Dave, and he's a builder. He builds houses for a living, and we discovered something today that might help us learn about linear expansion. So Dave, what's this thing here?
Vinyl siding. Fairly common. Find out around on the houses around here quite a bit. It's fallen into a little bit of disfavor with some other products that have come out, but you still find it you can put on the houses around here.
So you just put it on the side of the house and you nail it on?
Yeah, it just kind of clips. You look back here, there's a little lip. It clips right into here. It's real easy to put on. You just you put the nails in the holes here.
So what's with the long holes? Why aren't there just round holes?
Oh, well, vinyl will expand and contract with the temperatures. So like right now, I don't know, this is 10 degrees or something.
Well, I have a thermometer here. Looks like it's 12 below Celsius out here.
Okay. So, this thing is probably shrunk up about as much as it's going to shrink. So, let's say you put it on in the summertime and it's 80 degrees out.
Okay.
Yeah! Well, this thing's going to move quite a bit when we get to wintertime. And we drop, 100 degrees. So we have to put the nails in, and we have to be sure we don't put the nails in too tight. So we have to allow the siding to move.
Oh, I get it. So because there's a slot here instead of a hole, as the siding expands and contracts, it can just slide along the nail rather than being pinned to the house.
Exactly. And if you look at each end of the siding, this rib here on the top is cut back on both ends.
Okay.
Okay. And again, that's because the siding will slide back and forth, and you don't want the siding to hit this and bind, or then the siding will buckle under the pressure.
That makes sense.
So, and you have to make sure you can see quite a bit of overlap here, because again, if you put it on in the summer when it's fully expand it. In the wintertime, it'll contract, and then you'll get this gap when you're sighted, which, unfortunately, I see all too often.
Well, hey, I'm wondering if we could take this inside your shop, because I know it's heated, and leave it sit there for a while and see how much this thing grows.
Sure. Do you want to measure it before we take it in?
Let's do that.
Okay. See what length we have right now.
Well, Dave, let's take a look at how long that piece of siding is now that we've been in the heated shop for a while.
It looks like we've got 149 and I would say 25-30 seconds.
Let's use what we learned in that video to find the coefficient of linear expansion for vinyl. Here's what we know. We know that the change in length is equal to the coefficient times the original length times the change in temperature. So if we wanted to find alpha, solving for that, we could do this. We'd find that alpha is equal to the change in length divided by the length times the change in temperature. Well, let's first of all figure out the change in length. When we first measured the length of the piece of vinyl siding outside, it was 149.5 inches. When we measured the piece of vinyl siding inside after it had warmed up, we found that it was 149 and 25/32 of an inch. Now let's get this in decimal form so it's a little easier to work with. Obviously 149.5 is 149.5 inches. 25/32 turns out to be 0.781, so 149.781 inches was the final length. So when you put these two together, we get our change in length being equal to 149.5 taken away from 149.781 inches. And that comes out to 0.281 inches. That's the total change in length. Now, what was our change in temperature? Outside, when I took the temperature, I noticed that it was negative 12 Celsius. Inside, the temperature from the thermometer laying on the piece of siding showed that it was 24 degrees C. So if I subtract 24 from negative 12, I find out that I got a 36 degrees C delta T. So here's alpha. Alpha is 0.281 inches, that's delta L, over the original length, which is 149.5 inches, times our delta T of 36 degrees C. Inches as a unit go away, and so our units are going to be just per degree C, or per kelvins if you'd like, and the alpha value is 5.24 times 10 to the negative fifth. Now if you think about it, this is in the range, 10 to the minus fifth is approximately in the range of other things that you've seen from other references. It's a little bit bigger than some of the metals that you've seen, and I guess you'd expect that